Hello and welcome back to the second part of the teaching video on how to crystallize. In this part, we're going to go through the vapor diffusion setup and its phase diagram. There's two things that are required for crystallization to occur. These are supersaturation and nucleation. I will be defining these as we go along. The important thing to remember is that supersaturation is absolutely necessary for crystallization to occur, but it's not sufficient in itself. It's one of those necessary but not sufficient things in life. The second thing you need is a nucleation event. Now, what exactly is nucleation? The definition here is it's the formation of a critically sized cluster, or what we call a nucleus, a cluster of biological macromolecules in this case. There are two things to remember about this nucleation event. The first is that it's a random event. It's stochastic. There's absolutely no guarantee that it will happen. The only thing we can do is make sure that we promote conditions that will favor the nucleation event, but we can never force it to happen. The second thing to remember about nucleation is that it always involves a lag phase. Once the drops are set up, they are equilibrated. We'll come to that in a minute. You have to wait. This waiting period can be anywhere from minutes, although that's unusual. It can be anywhere typically from a day to months. It might even take longer than a couple months for this nucleation event to occur. It may never occur in your lifetime. There's always a lag phase before the nucleation occurs. But nucleation can only occur in supersaturated solutions. Why is this? Why is the supersaturation this necessary, but not necessarily sufficient condition? I hope in this slide that I can show what it is that's happening. In supersaturation, it's only then that we have enough molecules in solution to promote the accidental coming together of a few of them, and they stay together and build a critical nucleus. In an undersaturated solution, there simply aren't enough molecules there for that to happen. In a supersaturated solution, the molecules are very crowded, and so they're always coming together, coming apart, coming together. They might hit each other here and there, and at some point, maybe you get this lucky event, a nucleation event, where it's energetically more favorable for the cluster to stay together than to come apart. Supersaturation is a state in which there are more molecules in solution than what the normal solubility would allow at those conditions. An example is honey. Honey is a supersaturated sugar solution, and you sometimes see crystals coming out of the supersaturated honey. You may have noticed that. Another example is a soda pop. Carbon dioxide is not soluble in water at normal pressure, but you put it under pressure and then you can get a supersaturated solution. So those are two everyday examples of supersaturation, and it's also what we're trying to do with our protein solution. We got to get it supersaturated. So that leaves us with the big question, well, how do you get the protein solution into a state of supersaturation? Essentially what we are going to do is have controlled dehydration. We're going to manipulate the water of solvation. As you can see in this picture of a salt basin, taken at some national park in the U.S. The salt is crystallizing simply because it's out in the sun and it's dehydrating, and the salt comes out of solution in the sun. Now, why don't we pour our protein solution out on the lab bench and let it dehydrate like that to form crystals? This isn't going to work with proteins. They will denature. You have to treat them very gently. All proteins or molecules are surrounded by a hydration shell of water. For example, for myoglobin, which was the first protein structure ever determined, there's a 5 angstrom thick water shell around it. One molecule of myoglobin has 2,000 water molecules surrounding it. So what we do in crystallization is we manipulate this, one way or another, we manipulate this water shell that is around the protein molecules. We got to get rid of the water so that the protein molecules can come together with each other and form a critical nucleus. Now, how do we do this? We have 3 classes of precipitants that will manipulate the water in different ways. If you remember from the first part of the video, I mentioned that precipitants are the chemical entities that we use to derive the protein out of solution. The first of these precipitants that we use are salts. And anyone who's familiar with protein purification knows about the salting in, salting out phenomenon. Meaning, if you have a protein in solution and you add a little salt, it becomes more soluble. Add a little more, you can get even more protein into solution, up until a certain point. Then, if you keep adding more salt to the protein solution, the protein gets less and less soluble and it crashes out. It precipitates. This is the salting in, salting out. The salts manipulate the water of solvation by competing with the protein for the water. There just are not enough water molecules to go around if you keep adding salt. And so something has to give. Something has to come out of solution. And usually it's the protein, because salts are more soluble in water. The second class of precipitants that we use, and in fact this is the most common one nowadays, are polymers called polyethylene glycols. We call these PEG for short. These work by a bit different mechanism. They work by volume of exclusion. Polyethylene glycols are long flexible chains of glycols, and they thrash around like long spaghettis in boiling water. They thrash around in solution. Now you can imagine that if these molecules are thrashing around, the protein molecules are going to want to get out of the way. Think of a propeller. As soon as the propeller starts, you want to get your hand out of the way fast. That's volume of exclusion. And so that's how these polyethylene glycols manipulate the water shells around the protein. The protein wants to get out of the way, and it might then crowd together in a favorable way that forms the nucleation event. The third class are small alcohols, and they manipulate the dielectric constant of water. Water, H2O, has a very high dielectric constant, and by lowering it with the addition of small alcohols, the molecules of protein will come closer together because of it disrupts the shielding effect of the water around them. These 3 classes are not mutually exclusive. In fact, we often combine them. We mix the polymers with the salts and throw in some small alcohols. We use them often in synergy with each other. Okay, so how do we actually set up the experiment? The one that we're going to be talking about today is vapor-diffusion setup. It is by far the most commonly used one. There are other methods, but this is by far and away the most common one, both manually and with automation. You can set these vapor diffusion experiments up either as hanging drops, which is usually manual, or sitting drops. It's easier to automate sitting drops, but the principle is exactly the same. So let us begin by, of course, getting our pure protein. How much do we need? A good starting point would be about 50 to 100 microliters of protein at a concentration of, let's say, 10 to 30 mg per ml. That's very typical. It might even be as low as 2 mg per ml. Maybe you would need 100 mg per ml, but a good starting point is around 10 to 30 mg per ml. Now we're going to set this up as a manual setup, so we'll use rather big drops. We're going to use a 5 microliter drop and put it on a cover slip. Now over here in the containers, we have the precipitant. Today we're going to use 2 molar sodium chloride as an example. And we mix a quantity of the precipitant with the protein, and that gives us a 10 microliter drop. This is still a sitting drop, but now we're going to flip it over so that it can equilibrate with this precipitant in the reservoir. The reservoir, this precipitant, because it's in the bottom of the experimental tray, goes by many names. Some people call it the reservoir solution, some people call it the screening solution, the precipitant. It's all the same thing. It refers to this here. Now we seal this system. If we're doing it manually like this, we can use vacuum grease to seal the system so it doesn't just dry out. We want to have controlled dehydration. Or if we're using the plates that I showed with the auto crystallization robot, then we seal those plates with PCR film. But we seal it somehow. Now at the start, what is our protein concentration now in this big drop? Well, it's going to be half of the starting concentration, and this will also be half. What's going to happen? We have a closed system, and therefore we're going to have diffusion from the lower concentration of salt to the higher concentration of salt until they're in equilibrium. What happens is, goes by diffusion. Water in the droplet here, or any other volatiles you might have there, will leave the drop and join the actual vapor phase here. The water becomes a vapor and then joins the bulk water in the reservoir solution. So remember, the protein doesn't leave the droplet. It's the water molecules, the water of solvation, that is leaving the droplet. And this diffusion process continues until the concentration is the same now as here as it is down here. That's diffusion. And we call it vapor diffusion because it involves this vapor phase. So at the start of our experiment, we have a big drop of 10 microliters and this concentration. After equilibration, after the vapor diffusion, the droplet is going to shrink. It's now 5 microliters. This has two effects. The salt is now the same as here in the reservoir, but the protein has also become more concentrated. And we hope that by concentrating it, we have driven it into a state of supersaturation. If we get a nucleation event and the crystals grow, something else happens in this drop. The salt stays the same, but the protein concentration in solution decreases to approximately half of what it was initially. Now I'm going to present this experimental setup in a phase diagram. Crystallographers love phase diagrams because they are maps of what's happening in our droplets. So usually we have a parameter on the x-axis, some solubility parameter, and on the y-axis, we put the protein concentration. The important parts to remember are that we have the undersaturated state, where no crystal will ever happen in the history of the universe. And here we have the supersaturation. This is where we want to try to get our experiment. Now we can manipulate many different solubility parameters. We can manipulate temperature. We can manipulate the pH because that affects protein solubility. We can manipulate the salt concentration. We can do several simultaneously. We can make this, for example, a three-dimensional phase diagram, four-dimensional, but then it gets very complicated. So for today, let's just stay with a two-dimensional phase diagram to keep it easy for us. And here we will put the protein concentration on the y-axis and the precipitant on the x-axis. This supersaturated zone, which is pictured here in yellow, is a very unstable zone, and it has subzones where different things happen. If you go too high in supersaturation, yes, the protein will come out of solution, but as a disordered precipitate. You will get we don't want that. What we want to do is be in this nucleation zone where we get spontaneous nucleation. In the growth zone, the level of supersaturation is not high enough to support spontaneous nucleation, but it will support crystal growth. Let's look at this phase diagram now and plot our vapor diffusion experiment into it. So at the start of the experiment, after we've mixed the reservoir solution and the protein, we're at point A. How do we know that? Well, in our example, which we will also use in the lab today, with lysozyme, we've done crystallization of lysozyme about 3 million times. So we know that 1 molar sodium chloride at this protein concentration will be undersaturated. But if we take an unknown protein, a new protein, we don't know where it becomes supersaturated. That's where the screening process comes in. We have to test 1 molar, 2 molar, 3 molar. We have to test ammonium sulfate at 1 molar, 2 molar, 3 molar. That's what the big screening process is all about. So at point A, we are in the undersaturated zone, and you usually want to start undersaturated. Now, after equilibration between the droplet and the reservoir, the salt concentration goes back to 2 molar at B. Now, people sometimes ask me, well, why is the arrow going like this? Well, because, remember, this droplet is shrinking. So the protein concentration is also going to go up. So we have two effects here. Both the protein and the salt increase. If we're lucky, this B occurs in the nucleation zone, and we get a nucleation event. Crystals start to grow. And they will continue to grow until they reach point C. The crystals are in the solid phase of the protein, and they will deplete. The growing crystal is a solid phase. It will deplete the liquid phase of the protein, and that's why the protein concentration actually goes down as the crystal grows until it meets this solubility limit at C. This is a very important black line. This is the black line representing the limit of solubility. In other words, at C, the number of molecules joining the solid crystal are the same amount of molecules of protein leaving the crystal. So there's no net growth. In fact, the crystal stops growing because at C, the solid and the liquid protein phases are in equilibrium. How long does this process take? Once again, The equilibration with the reservoir solution takes about 24 hours for salt to equilibrate. If you're using polyethylene glycols, it can take 3 to 4 weeks. But how long does it take for the crystal to grow? Well, as I mentioned, there's always a lag phase for the nucleation event. Now the crystal will stop growing because there's no more liquid protein to feed it. This is one reason why the crystals stop growing. There's a second reason why they will stop growing, and that is because of something called mosaicity. The growing crystal lattice should pack nicely, but in reality, that seldom happens. The droplets are full of other kinds of things. They're full of pieces of dirt that fall down, or you haven't filtered your buffers properly, or sometimes the protein molecules are not homogeneous with the growing lattice. Maybe a few amino acids are nicked off the end of the C terminus or the N terminus. So what happens when this dirt or heterogeneous molecules become incorporated in the growing crystal lattice, the crystal lattice becomes disturbed, and eventually it becomes so disturbed, so disrupted by the dirt and heterogeneities, that the crystal stops growing for that reason. This is called mosaicity. It also will affect the diffraction pattern. Mosaicity is a bad thing. You don't want it. So if you remember, in the first part of the lecture, I mentioned that we have to have good crystals. They have to diffract to at least 3 angstrom. But a big reason why they don't is because of mosaicity, imperfections in the crystal. Okay, today I've had an opportunity to talk about 1% of everything there is to say about protein crystallization. The other, now I'm going to make a shameless plug for my book. The other 99% is in one of my books. And you can also read more on my website. I hope I've done a good job of explaining these concepts, the vapor diffusion, nucleation, supersaturation. I hope I've been able to explain these concepts to you today. But if you think, I have no idea what she's talking about, don't worry. I can recommend some literature for you to read. These are available as part of the course literature, or you can download them yourself from the internet. McPherson and Gavira explain these concepts in one way, and Nir Asheri explains them in another way, completely different from both of us. And between the three of us, I hope you'll be able to understand these concepts on how to crystallize. So let me sum up here. I hope you remember lots of things from my lecture, but here at least are what I consider the big 3. I'd like you to remember why proteins are hard to crystallize. I'd like you to remember that the 2 critical steps that are involved are supersaturation and nucleation. Finally, I'd like you to be able to draw the parts of a phase diagram and put these into it. All right, I thank you very much for your attention. I wish you good luck on the exam and with all your crystallizations. Thank you.